Hi, good morning, everybody. I see a lot of familiar faces. It's good to be here. And as Tanya said, I'm here to talk about OpenCL vectorization. OK, so first of all, let me talk a little bit about our team. So I work for Intel, and my team is responsible for the OpenCL SDK. So we develop the compiler for the OpenCL SDK, the debugger, and the runtime, everything, the profiler, everything that's part of the SDK. We have an offline compiler. And the team is located in Haifa, Israel. And we're also responsible for improving LLVM and supporting future Intel architectures. And it's a really small team, and we do everything. It's like a small startup within the company. And these are really exciting times to be in this team, because OpenCL is developing an LLVM, and it's really fascinating to be in this team. And this is our product. This is the OpenCL SDK 1.5, and we support the 1.1 spec. We support Windows 32, 64, and Linux 64. We have a unique implicit vectorization module, which I'm going to discuss today. And it's available online for free. We have a nice website. You can go online and download and play with it. It's a really good product. We're proud of it, so give it a try. And this is one of the tools that comes with our SDK. This is called the Intel Offline Compiler. And in the box to the left, you can copy and paste OpenCL code and click Compile. And to the right, you'll see LLVM IR. So you can look and see what's going on under the hood and try to optimize your code. Some people feel more comfortable looking at LLVM IR than assembly. We support both x86 assembly and LLVM IR if you want to optimize your code. So it's a really nice tool, and we have demos online on how to use this tool. If you click on the link later today, you'll see different videos, and it's a really nice tool. So as you can probably guess, our OpenCL compiler is based on LLVM. We use LLVM as our compiler. So let me talk a little bit about OpenCL and what it is, really. So OpenCL is a framework. It's a framework for programming GPUs, CPUs, DSPs, and other acceleration devices. So it's a unified programming language and a framework. It was proposed by Apple, and now it's controlled by Khronos, which is the same organization which controls OpenGL and other standards. So it's an open standards with members from different companies in the industry: Intel, AMD, Qualcomm, Apple, of course. The language itself is similar to other data parallel languages, similar to graphic shaders that you that computer games use, such as DirectX use graphic shaders. But the language itself is a C-based language. It's based on C99. And OpenCL calls the shaders compute kernels. And these compute kernels are C99 based. They have some restrictions. So for example, you can't use recursions in the 1.1 spec. You can't use function pointers. And so you do have some restrictions, but you also have places where the spec is extended. So for example, there's new data types in the OpenCL language. You have the float 4, for example. This is a type that OpenCL has, which represents a vector of 4 floating point numbers. And you have other types, short 2, etc. And the OpenCL spec also defines a rich set of library functions. So for example, you have the sine and cosine functions that you can also find in the C spec, but you also have sine4, which works on the float 4 type, which means that it computes the 4 sine operations on each one of the elements in the vector. And the spec also defines the precision for each one of these functions. So it's a very verbose spec. And it's a very nice language. So it's very similar to CUDA. If many of you are probably familiar with CUDA. OpenCL is very similar to CUDA. So on the screen here, you can see OpenCL kernels. So to the left, you can see a regular C program, very simple. It's a for loop. We go from 0 to n, and we multiply values from array A and array B. And this is great for targeting CPUs. But if you want to target a GPU and other devices, then you would need something else. So data parallel languages kind of have this notion of this implicit outer loop. So basically, instead of writing a loop from 0 to n, you write this kernel, this compute kernel, and instead of accessing the variable I, you access this function, get global ID. And you actually specify the dimension here. You can have several dimensions. And then OpenCL defines this partition of the workspace. So let's say that we want to work between 0 and n. These are the different iterations that we execute. So this is the workspace, and OpenCL kind of breaks it down to work groups. CUDA calls it blocks. OpenCL calls it work groups, and each iteration in the original C code is called a work item. And each kernel works on a single work item. So instead of writing the entire loop, you can just write A at ID times B at ID, where ID is the get global ID. All right, so how do we vectorize it? I think it's pretty obvious that we want to vectorize it in order to boost the performance of these workloads. So first, let's see how we execute it without vectorization. So basically, the OpenCL runtime is responsible for executing these compute kernels on each one of the work items. So, and serially, I mean, you execute the work kernel on the iteration, on the first iteration, the second one, and et cetera, and so on. And basically, you just run the code, and it's really easy to implement. But what we'd like to do is vectorize. And this is totally completely different than auto-vectorization of C++ programs. In C++ programs, you vectorize the innermost loop. In OpenCL, you do something completely different. In OpenCL and data parallel languages, you basically modify the kernel, and you make it work on several work items at the same time. And then when you work on several work items at the same time, hopefully, if your new kernel runs faster than the original, or faster than processing several work items one after the other, then you get an increased performance. Just because you need to execute the kernel less times. Now, let's look at it from another perspective. So we have the original kernel, and this is an LVM conference. So the first thing that we do is we convert it to LVM-IR. And then we do something simple. We take the, and by the way, this LVM-IR can contain function calls, arithmetic operations, memory operations, load, store, and all that, just standard LVM programs. And we widen each one of these instructions. So if we had a scalar arithmetic operation, it will become a vector of operations, and we also need to replace scalar functions with a vector equivalence. And once we do that, we can simply reduce the number of iterations that we execute, and this is vectorization. So it's pretty simple. Something interesting to notice is that if we look at the SIMD vectors, notice that the first cell in the vector would always execute work item modulo vector size plus 0, plus 1, plus 2, et cetera, and so on. So it's very, I mean, you can look at the graphics from earlier and kind of visualize it. And this is how it looks from an LVM-IR point of view. We just take a scalar instruction and we widen it to a wider vector size. So this is vectorization of data parallel languages in general. So let's talk about the OpenCL vectorizer. So our product, the product that we ship, is the OpenCL SDK. And the vectorizer is one of the components within this compiler. So in this picture, you don't see the entire OpenCL SDK, just the compiler component in this. And similar to a lot of other LVM-based compilers. So at first you have Clang, and we took Clang and we added OpenCL support to Clang. A lot of the work was done by changing header files, but we didn't need to change a lot of Clang itself in order to add OpenCL support. And then Clang generates LVM-IR, and the LVM-IR goes into LVM, and we run the standard LVM optimizations, And we also have OpenCL specific optimizations and transformations. And the Vectorizer is a set of passes, is a group of passes which we use. Additionally, we have our built-in library, which is the functions that I mentioned earlier, sine, cosine 4, which is a big bag of LVM IR that we have on the hard drive. And then we load it, we link it, and finally, we take this LVM IR and we pass it to the code generator, and we use the LVM JIT to execute our code. Now, one thing that's interesting about the OpenCL Vectorizer, that it is not an OpenCL Vectorizer. It is a general data parallel languages vectorizer, and OpenCL is only one of the clients, one of the users that it has. So the Intel's OpenCL SDK is one client. We also had an internal product, a DirectX product, which used the OpenCL which used the Vectorizer to vectorize DirectX shaders. We also shared our Vectorizer with some of our partners. We also have other unreleased products. And our Vectorizer is also multi-target. It doesn't support, it's multi-language and also multi-target, target independent. It supports code generation for SSE4, AVX, AVX2, and other Intel architectures. So it's very flexible. Now, the way we achieve this flexibility is by hiding a lot of the different language and target information in separate analysis. So we have this language analysis pass that provides all the language details to LVM. So for example, the keyword that I showed you earlier, the get global ID, is unique to OpenCL. DirectX doesn't know what this function call means. And in DirectX, for example, you have the word sync, which is a synchronization mechanism. And there are other keywords that DirectX has and that OpenCL doesn't have. And also, each one of these languages have a rich set of built-ins that you need to convert and you need to widen. So sine becomes sine 4. And DirectX has a different set of libraries. And so all of this is embedded inside this language analysis, which is used by the Vectorizer in order to separate the languages from the Vectorizer itself. And LVM is a very flexible toolkit which allows us to do all that. Now, in the heart of the Vectorizer, we have the packetization. And really, when you think about vectorizing, you think about packetizing. So you take a single element, scalar element, and you widen it. That's pretty simple. But it's not, because there's a lot of different details that you need to account for when you actually packetize these things. So the obvious thing, take scalar, turn it into a vector, no problem. Function calls. Function calls could be very complicated. It's not only, go look in a table, find the equivalence function, widen it. You also need to take care of calling conventions and other problems. And load store operations. So the memory that we store or that we widen may be dependent on the index. Let's say we load A at I. Now, we need to have very sophisticated analysis to try to detect whether the memory that we're loading sits consecutively in memory, or can we issue a wide load, or do we need to use a gather, scatter operations to access this memory? So the packetization phase looks simple, but it's really complex. Now, a lot of our users use vector instructions in the code. OpenCL supports float 4 as an example to vector types, and a lot of our users use vector types. Now, how do you vectorize vectors? You can't create a vector of vectors. So the thing that we do is we scalarize the vectors, and then we vectorize each one of the components. And the idea is that users who use vectors usually use short vectors. Intel AVX support 8 wide vectors, which doesn't really fit a lot of programming domains. So for example, when you have color, you have 4 components, RGB and alpha. Or when you have coordinates, you have several components, and users write code for their problem domain. And so, but we want to make use of the wide vectors and kind of generate optimized code. So we advise our users, listen, if you want to use vectors, do it only because that's a problem you're trying to solve. Don't try to optimize your code, because we vectorize the code anyways, and we're likely to generate better code, especially when considering future architectures. Because porting vector code from one generation to the next is really complicated, usually. And by the way, this transformation is called AOS to SOA, at least for graphics, if you're in the domain of graphics. Now, packetization is not enough. You can't always just simply widen the instructions and expect everything to work. I mean, it'll work if you don't have control flow. But a lot of times, different work items take different control flow paths. So you need to predicate or create masks in order to generate correct code. Because the second that all of the work items take the same control flow, the same path, then you can widen everything and packetize it. But before, you need to flatten the control flow. So in the example here, you see that not all of the work items go the same path. If the index is greater than 17, then only then the value 7 will be written to memory. And we also need to handle more complex control flow, while loops, and etc. So predication comes before packetization. So the first step, the first thing that we do, and by the way, this is not LLVM IR, but just an example. We actually predicate LLVM IR and packetize LLVM IR. So the first thing we do is we calculate masks. So the condition that we had earlier, index greater than 17, becomes a Boolean, a symbol bit, which tells us if we need to, or if the branch is taken or not. Then in the next line, we use it to predicate the store that comes after it. So we have a masked store, and we save the number 7 to memory only if the condition is true. If the condition is false, then we don't do anything. And this code is correct. You can execute it, and you'll get the same result as the original code. The next stage is to turn the predicate into a mask. So masked store becomes mask store 4 because it has a 4 wide mask. So this is how the predication and packetization works together. Now, it's not that simple. You don't just take every if and convert it to a mask, because you have sometimes you have complex loops. Now, for a simple loop that goes from 0 to 256 and all that, you're guaranteed that all of the work items will enter together and leave together. But sometimes you have user code which uses a while. And in a while construct, all of the work items enter together, but they leave at different times. And to account for that, you need to generate a loop mask. So let's look at the loop mask. All of the work items enter at the same time, and every time a work item leaves the loop, we need to change the loop mask. And all of the instructions inside the loop need to operate using this mask. So if we have a load or store operation, then it only needs to happen if the mask is active. And the same goes for values that are calculated inside the loop and are used outside of the loop, and because they need to be frozen at a certain iteration. So we need to account for that. And it adds complexity and overhead to vectorization. But it's something that we need to do in order to achieve correctness of OpenCL programs. Now, how do we mask? How do we predicate instructions? So first of all, we need to predicate function calls for obvious reasons, because we don't want to call the function call if the work item is not active. We also need to predicate loads and stores, because we don't want to store junk to memory, or we don't want to load from an invalid page in memory, because we may hit a segmentation fault. And there are other instructions. For example, we can't divide by 0. We need to mask that. OpenCL runs with the floating point exceptions disabled, so we don't need to actually predicate every single floating point instruction, but we do need to predicate some instructions. And the LLVM does not support predication, and we had to work with that. So we basically implemented a very wide set of intrinsic functions for every load store operation, and we needed to write special code for widening these instructions and special code to add an addition argument to each function call, and we needed to teach 5 different modules how to handle the new call, and it's pretty complex from a software engineering point of view. But the idea is simple. Just add a predicate to the instruction, and it'll work. And also the analysis of predicated instructions is a little bit more tricky. So as I mentioned earlier, when you predicate, you take the control flow when you flatten it. So if you have an if statement, you execute both the then and the else side of the calculation. And one thing interesting is that if you have several work items that operate on this function, you have reduced vector utilization. So if you look at the example, and if you look at the blue square, only one of the work items had actually executed the blue vector operation, 1 out of 4. So it's not very efficient, but yet we did need to execute this. So we have reduced vector utilization, and also when we vectorize, we need to calculate different masks, and we need to store them in registers. So we have this overhead when we vectorize. So how do we handle this overhead? So the way we handle this is by implementing a vectorization heuristics, which decides what is the preferred vectorization width, vectorization factor. So it's like 1, 4, 8, or something else. 1 means don't vectorize, run the scalar code, which could be faster in some cases. Imagine a very complex set of nested ifs, one instead of another if, instead of another if. The vector utilization at the end will be very low, so you don't want to vectorize in these cases. But we also have other conditions in which it's better to vectorize for size 4 or size 8. For example, if you're familiar with the AVX instruction set, it mainly focuses on integers. I'm sorry, floating point operations. Integers are supported by AVX2, but AVX1 focuses on floating point operations. And if you see that your kernel is dominated by integer operations, then you're more likely to benefit from a vectorization factor of 4, because you don't need to take your big integer vectors and then split them in half and then put them back together and then split them in half again. So our heuristics decides that. And so the heuristics is a static analysis pass. We execute it in the beginning of the vectorizer. We gather different parameters and information, and then we make the decision of what's the vectorization factor that we want to use. And we tuned it using a very large number of OpenCL kernels. So the analysis is very, developing the heuristics is very complex, but tuning it is really easy. You just take a bunch of workloads from clients and programs that you find online, and you run them as scalar and as vector with 8 and vector with 4, and then you simply try to pick the best version, make sure that the client code would run, that the heuristics would pick the fastest version of the 3. Now, vectorization itself is a really fast pass. It doesn't take a lot of time to actually run it. The build time is not significant, but what is significant is the code generation build time, which is increased dramatically. So first of all, in OpenCL, the user may decide on the workgroup size relatively late in the compilation process. So we need to compile both the scalar and vector version and cogen both of them, which doubles the compile time. And also vector code tends to be a little bit slower. And so the compile time obviously increases. So we developed the OpenCL SDK, which is based on LLVM. And we also interact and work with the community, which is beneficial for us and for the community. So let me start with a short story about the vector select. So we have, in LLVM, we have the select instruction, and until recently, LLVM did not support the vector select variant of this instruction. So a select instruction is an instruction which selects between two values. In our case, we have A and B, two different vectors, and then we have the selector, which is a vector of bits, and if the bit is 1, you take the first one. If the bit is 0, you take the other one. And it's usually used together with the compare instruction. So you compare, then you select between two values. And until recently, LLVM did not support vector select. And so we had to implement this special pass to find vector select instructions, because our vectorizer and basically the predicator generated a lot of masks, and we needed to use vector select for these masks. Anyway, so we implemented our own pass to find vector selects and replace them with intrinsics, and then we needed to add support for more and more instruction sets, AVX1, AVX2. And so that wasn't a clean solution, and we really wanted LLVM to support vector select. And I was fortunate enough to work with Duncan Sands on actually resolving this problem within LLVM, which I recommend. He's a busy person, but I do recommend working with him because he's wonderful. So in this work, we added a new kind of type localization. Type localization is the phase in LLVM which takes illegal types and converts it into legal types, which can fit into physical registers. So in the example that you see right here, let's say that we have the original type 4 chars, 4 times I8. It obviously can't fit into a single register, and you need to somehow legalize it. So the old way of doing things was to add more characters until you fill the register, and the new way of doing things is to widen each one of the elements. And this is something that was needed for the implementation of vector select. So it's now enabled in the LLVM trunk. It didn't make it to the LLVM 3.0 release, but if you go to the top of tree, then you can use it. And by the way, so once the vector promotion was in place, on top of that, I implemented the cogent support for AVX, SSE4, and I used the emulation for other targets using vector XOR and so now you can use that. Now LLVM is a wonderful toolkit, but it's not perfect, and we want to make it better. And so here's a wish list of things that we want LLVM to change. So the most important thing for us is the support of predicated instructions. We vectorize, and we know that just by looking at the industry today, it seems like more and more architectures are focused on vector architectures, and we'd like to support these architectures. And we'd like LLVM to be able to support predicates and masks natively, which is something that we need to discuss as a community. Something else is the support for Windows. So a lot of times Windows is not supported as well as Mac and Linux. And it's understandable. I mean, most of the LLVM users come from these two platforms. But our product is, or we do support Windows. And just the problems that we encountered is the different calling convention and the MC infrastructure and the build system, and these are things that we had to fix locally. And backward compatibility of IR. So the OpenCL folks propose to use the LLVM IR as an intermediate IR for OpenCL. And there's been some discussion in the mailing list about this. And in order to achieve this support, we'd like to work together with the community and kind of make LLVM more portable so that we can actually build on top of this IR. And once we do that, we'll need to support different versions of the LLVM IR, because the OpenCL spec will continue to move forward, and so is OpenCL and LLVM, and we'll need to migrate easily between different versions of LLVM. Now, we've been working with the community. We released some bug fixes and features to the open source. Now, we developed AVX support internally based on LLVM 2.8. And other people developed AVX on top of the trunk, the LLVM trunk, at the same time. But we needed to deliver a product, and we didn't know exactly when the work on AVX will be finished, so we needed to develop our own AVX version, which is not the way to do things. So in the future, we're going to work closer with the community, and this work had already begun with AVX2, and we're more involved, and also we're going to release, or started even to release, our changes or improvements to LLVM's AVX, which came from our branch. And just to give an example, Windows calling convention for AVX and better shuffles and JIT support for AVX are all. We started releasing these things, and in the future we intend to work closely with the LLVM community to better support future Intel architectures and make sure that LLVM has the best support for these architectures. Thank you. I'll take questions now. Yeah, it's okay. Yeah, go ahead. I'm sorry? No, I can't. Yes.
Can you do a little comparison between your vectorizer and the work that's being done in the data parallel image?
I'm sorry, I'm not familiar with the work. Well, first of all, I didn't hear the whole.
Can you give a little comparison between the vectorizer that you guys have for OpenCL and the Intel data parallel image that's just been released recently?
I'm not familiar with this product, so I can't make the comparison. Duncan.
How do you handle
Vectors of pointers. We don't. We scalarize. How do we handle vectors? How do we handle vectors of pointers? So we don't have a good solution for vectors of pointers. We do have ad hoc solutions inside some built-in functions. So for example, we can bitcast the pointer into I64 and use that. We also have other solutions. Sometimes we detect that we access base pointer and offsets, and in that case we abstract it using a function, and then we packetize this function or predicate this function. It's not clean, and it's something that we need to solve. Yes?
So Intel hardware is multi-core, and you didn't talk about any thread level parallelism. Is that in the product or planned?
Yes, it's in the product. We use TBB, thread building blocks, to execute on multiple cores. Yeah.
When you talk about your vector instructions, what about the GPU? Do you do anything provided to the GPU?
I can't talk about unreleased products. Yes?
So does OpenCL have the concept of reductions, and so does your vectorizer support those?
Our vectorizer does not do anything in the area of reductions.
It's more of a comment than a question. I'm really pleased with the contribution you guys made to the AVX support. LLVM Victor stability and is something I think we really should shoot for. And I think 3.0 is a good basis for that. I would say it's stable from here on out. That's great. One of the big challenges, though, is the testing aspect. How do we make sure that we don't accidentally break? Do you have any thoughts on that?
No. I don't. I mean, it's a good point. How do you test it? How do you make sure that?
We cannot intentionally break it, but how do we make sure that we don't accidentally break something?
Right, and I also understand that there's a contradiction in what I said. I mean, on one hand, I want the LLVM to be stable. On the other hand, I want the LLVM to support predicates, which it currently does not. So, yeah, I agree.
They're not inherently intentional. I mean, in the 1.4 timeframe, we were stable across the ecosystem. 3.0, I know this is. I think 3.0 is a really good basis to provide stability from. I mean, I think we've certainly sorted out a lot of long-standing issues.
That's a good point. Thank you. Any other questions? All right. Thank you.